So I think we'll get started with the webinar right now. So yeah, welcome everyone to our 4th episode of the MYMI webinar series. My name is Evan and I'll be your host today, and behind the scenes for Father will be moderating discussion. So our topic for today is AI in medicine, and we're joined by Dr. Seah. So welcome to the webinar. Thanks for coming in today.
Thanks Evan for the introduction. My name is Dr. Jarrel Seah. I'm a medical doctor and radiology trainee at the Alfred Hospital in Melbourne. I'm also a deep learning engineer and medical AI specialist at Harrison AI. And I've also previously worked in the MedTech space in a variety of other companies, and also participated in several MedTech competitions.
So I think we can just head into our first question today. So I'll just starting just to sort of get a better idea of like how you got to where you are now. Like, could you sort of describe any like inspirations or experiences that actually like led you towards working in AI and radiology in particular?
Yeah, sure. So I guess for me, my first contact with AI really was back in university when I was a medical student. I took a year off to do an honors degree in Bachelor of Medical Sciences, which is a 1-year honors project. And my honors project was basically about detecting cervical spine fractures on X-rays, which are notoriously hard to find, and so it's a topic that a lot of people was working on. And I remember spending about 9 months really working on this. And then in the 10th month of my research, this is 2014, 2015, and then this news comes out on Reddit saying, look at this ImageNet winner, IOVRS 2014 winner, which is this convolutional neural network that beats everything by like 10%. And then so immediately everything I did for the first 9 months of the year was wasted, because I was sort of using the previous, sort of the old style computer vision techniques, like histogram of oriented gradients and Radiology object detection framework, graph cards, that kind of thing. And so really, ever since that point, deep learning was kind of the thing that I was interested in. I've always been interested in computer vision specifically because it seems like such a simple topic, but until very recently, in the last few years, humans have really not been able to do very much with it. So I guess that was my first contact with AI back in the day. And ever since then, I've been working on different approaches and how to integrate that into medicine. And there's just so many things that you can use AI for in medicine.
And I think we can just head into like our topic, which is AI medicine. So, could you sort of just give a broad instruction of what AI sort of is, just for those who don't know what AI is, and sort of like talk about how
sure. So AI obviously is a bit of a loaded term. We call it artificial intelligence, but there's a saying that says there's this thing called the curse of AI, which is when something when somebody builds something that's true, what people would consider AI, the goalposts shift. So back in the pre-2000s era, when somebody built Deep Blue, which beat humans in chess, they went, that's not AI, it's just searching. And then obviously Google's PageRank algorithm is pretty amazing, right? It searches millions and billions of web pages and gives you the correct answer most of the time. You never go to the second page of Google search. And if you went back in time and you said to somebody in 2001 and you said, I'm going to have this search engine that can search through 1 billion web pages, and they were like, you're insane. That's like, you'll never be able to do that, right? So the curse of AI, I guess, is that whatever the computer can do is considered to be not AI, and I guess today that's sort of getting a little less pronounced as AI sort of re-enters the mainstream, and this has happened before, right? Because I'm not sure if you guys have heard of before this, but there's this thing called the AI winter, and there's actually 2 of them back in the 1960s and 1980s. the first wave of AI was this sort of symbolic AI where people just basically got a whole bunch of if statements, right? And then that didn't work. So after that, people said, that's not really AI. And then after that, people went and did all this neural network stuff. And they said, that still didn't work. So they said, that's not really AI. It doesn't capture intelligence. And now it's only today when we've got enough data and enough computing power to really make something that has got human performance and a lot of things. And people actually say, no, maybe that's AI, right? I prefer really to use the term deep learning. And that really refers to the modern technique of getting lots and lots of neural networks and stacking them on top of each other and then feeding them an incredible amount of data to produce results that would previously be considered impossible for computers to achieve in terms of vision, speech recognition, any kind of data that is unstructured, like images or sound. Processing that using deep learning is basically the state of the art in many, many different areas at the moment. I think in terms of how AI can help medicine, a lot of data in medicine is unstructured, as you probably know. There's a lot of images, a lot of sounds, a lot of inputs to the clinician comes in unstructured. And that's one of the reasons why, up until now, medicine has basically remained, for all intents and purposes, from the process management point of view, a medieval process. People say that doctors are basically apprentices. Right? They work in a environment where one doctor can only treat one patient at a time. Right? You can't have one doctor treat 10 people, right? You can't have a factory line of doctors, and you can't improve their efficiency. And that's because all the data that the doctor ingests is all unstructured, right? They look at images, they talk to patients, they deal with text, they deal with speech, right? They don't deal with Excel spreadsheets, right? And no patient comes to you with an Excel spreadsheet of symptoms. So, that's the thing, right? So that's why up until now, medicine has been a practice, right? People practice it, they're apprentices to other doctors, and they learn their trade, and then at the end of it, you spend 10 years and you've got one guy who can maybe see 1,000 patients a year. Right? And so that, because of that, you can have a chronic shortage of doctors. And I think AI really sort of is the next industrial revolution, right? It means that we can take tasks that would have been, very, very repetitive intellectually, and just automate them so that you don't have to think about them. And you can just do the top tier stuff, and you can see multiple patients at the same time.
Can you give any examples of how AI can actually solve this issue of not being there not being enough doctors?
Yeah, so here's a really good example, right? Radiology, which is the AI, the area that I'm working in, is probably the most prominent example of this. Radiology started off as basically photographs, right? You take photographs of a patient with X-rays. That's what radiology used to be. And then you had a film, you developed the film, and then you took the film to a light box, and then someone looked at the light box and said, there's a cancer there. Right? And obviously this is super repetitive, right? And it means that somebody has to look at every image, right? And today that's still the case, right? Every single image that we take in radiology has to be looked at by somebody. And that's a problem because imaging is getting more and more accessible. It's getting cheaper and cheaper. I think some estimates say that the volume of radiology studies or images doubles approximately every 3 to 4 years, right? And that's clearly not sustainable because the number of radiologists you have aren't doubling every 3 to 4 years, right? So that means that radiologists have to look at more and more studies, right? And at some point, the human becomes the bottleneck, right? We can build more machines, we can build more CT scanners, we can build more MRI scanners, right? We can put more patients through those things. But for someone to actually look at the scan and say, you have this disease, right? That's going to become the bottleneck. It really is the bottleneck in many cases. So and that's the most obvious area for AI to basically come in. No.
Yeah. Can you talk more about sort of how you kind of solving those sort of problems at the moment, working in radiology in particular, how you sort of trying to use AI to actually solve these problems?
Yeah, so the ingredients for every building any AI is data. as you probably know, as I alluded to before, it really isn't, nothing has really changed, right? The neural networks that people use in the 1980s, most of those techniques are still around today, the same techniques. There's been maybe a few algorithmic improvements for efficiency, but the main change is the fact that people play a lot of games, and so we've got really good graphics cards, which are really good parallel processors. And then the other change is that we started digitizing everything, right? Like people started taking photos of literally everything in the world, and so that means that you have enough data and you've got enough compute, and so that gives you a good algorithm, right? So that's how how you go about building an AI. But building AI algorithms isn't the hard part, right? In any case, in almost every case, if you can define your problem space in the form of inputs and outputs, this is the input image, this is the output answer, whether the answer is a circle the pixels, or tell me where something is, or tell me if something exists in the image, or if it's a picture you want to convert to another picture, you can do that too. You take a picture, you can convert it into sounds if you wanted to. As long as you have enough input and output pairs to define your problem, basically any problem is solvable with deep learning. Almost. Obviously, there's some exceptions there, but if you've got enough data, by and large, it's a solved problem. So the question is, to actually build something that's useful, you need to answer the right problem, right? In the past, we used to say that the problem is a problem statement, right? It's how do we do X, Y, Z? Right? How do we read a chest X-ray? Right? In this case, I put it to you that the problem statement actually isn't a statement; it's a data set. Right? This is all the examples of the stuff we want to detect, right? How do we go about detecting it? Right? And the big challenge is structuring that data set in a way that's clinically useful, and basically answering the questions that clinicians want, right? So I'll give you a really good example of how somebody didn't do this right. So there's about 3 years ago now, one of my friends released a data set from the NIH, Professor Ron Summers, which released this data set called chest X-ray 14, which is a huge data set, 110,000 chest X-rays with lots and lots of pathologies. One of them is something called a pneumothorax, which I'm not going to go into the details of, but essentially it's a life-threatening condition with air inside your chest where it shouldn't be. And the treatment for that is to put a tube in and drain it. And so people said, that's easy. The problem statement is obvious, right? The input is the chest X-ray, and the output is there or is there not a pneumothorax? Binary outcome, right? So a whole bunch of deep learning engineers rush out and build these great algorithms that claim we can detect pneumothorax with 99% accuracy or 0.99 AUC, right? Sounds really good until you realize that all they were detecting was whether or not there was a chest tube in the patient, right? And because the trick is, when somebody has a pneumothorax, you put a tube inside to drain the pneumothorax, and you can see that tube in an X-ray. So really, the question you should be asking is not, does the patient have a pneumothorax? It's, does the patient have a pneumothorax without a chest tube? Because those are the ones we care about, right? Clinicians don't care if you can pick up a chest tube and you only pick it up if it's a chest. You only pick up pneumothorax when it's a chest tube. Like, that's useless. That's like saying, we've picked up the pneumothorax, but I've already treated the patient, so that's useless. Right? So then the key point is, it takes a lot of effort to construct these data sets, and these data sets are the problem definition. And so you need to speak to people who are going to use these algorithms, work out exactly what is it they need to solve, what is it they have to detect, or what they have to find, what they want to do, and then you can construct your data set in a way that's useful.
And could you talk more about sort of the actual process of, using AI, to solve like issues in radiography? Sort of just for someone who might not really know much about AI, how does the researcher actually, use it?
Yeah, so AI, like I said, is really good at taking in images and producing outcomes, right? Or taking in unstructured data and producing outcomes. And one sort of thing that a lot of people are using now in terms of AI for radiology is things like denoising. So if you think about it, denoising, like when you take a photo in a room, right, and there's no light, for instance, it's very dark, you can't see anything. You can use AI to process that photo as if you were taking it in a bright light situation, right? And lots of Google phones do that. These phones, if you notice, with every software update, seem to be getting better at taking photos in low light conditions. The hardware hasn't changed. All that's changed is just someone's come up with a fancy neural network that takes in an image and produces another image based off the first image that looks better. It's post-processing. It's Photoshop. It's auto Photoshop. Right? And a lot of people are using this in radiology. Right? So you take a scan, a CT scan, for instance, right? Patient moves during the CT scan, it gets very blurry, or the patient's very big, there's not enough photons, and it's sort of like the equivalent of being too dark. And so it's very hard to find pathologies in that case. And so people are using AI to basically do the equivalent of reconstructing that image as if the patient hadn't moved, or as if the patient had enough photons. And this is really important because taking images twice in radiology, taking images twice on your phone is fine, no one cares. But taking images twice in radiology means double the radiation. It means that you have to keep the patient there for longer, and it also means more cost. So it's obviously a good thing all around if you can avoid that.
So in terms of radiography, like what are sort of like the biggest barriers at the moment in actually like implementing like AI in radiography?
Yeah, so the use case that I said before is a lot of people are jumping at it because it's easy. Right? It's immediately obvious. The input is noisy image, output is not noisy image, right? It's obvious. The other places where people are having more trouble with are the clinical stuff, right? When you, like I say, you're trying to detect particular conditions. And I think that's the big barrier, is that a lot of companies that are trying to build AI tools are building them in isolation from the clinician. So, they go and find a data set that has these pathologies and says, we can detect these pathologies too. And it turns out in many cases, that's really not the thing we want, right? It's sort of like saying, when you look at an image, right, and you're trying to describe, you're trying to, an image on Facebook, right, let's say, you're trying to tell whether or not this is useful for your profile picture, right, or something like that. You're taking a photo and saying, this is a good photo, right? Instead of saying, this is a good photo, a lot of companies are basically just saying, I can tell you whether it's morning or night. I can tell you one very specific thing about this image, right? Which, is completely like not very useful because we look at so many other things the image is intact. Right. So a lot of companies come up with, one specific thing that they look at. So they say, I can detect pneumothorax, but you can't detect that it's a chest tube. So that's useless. Right. So that's the big barrier, is that people come up with these isolated solutions, which are technically very good and very accurate, but because they don't detect anything else, or they don't solve enough of the problem, there's not much incentive to use them. Does that make sense?
Yeah. So like sort of the biggest issue is actually, those companies not actually consulting, the people actually use technology.
Exactly. Yeah, exactly. They're not finding, a use case where you've sat down to the clinician and said, all right, if it could do X, Y, Z, would this be useful to you? What else would it have to do for it to be useful? Right? You're not sitting down and saying that. And they're coming up with these sort of more data-driven things, right? By saying what's easy to label, right? Like you can go out and say, oh, it's very easy to get pneumothorax because there's so many public data sets that I can use, right? I don't have to go and rebuild that. And then so they're looking at it from the data perspective, say what data do I have, what algorithm can I make, and then what can I sell, rather than going the other way and saying what's the problem I'm trying to solve, how do I solve it, and then what data do I need to solve that problem?
Okay. So I think we can move on to our third question. So I'm just wondering, so where do you actually sort of see like, AI in healthcare, like heading into the future? Like what are the sort of like, sort of like, what sort of big sort of advantages do you think AI can actually like make sort of in the next few years?
Yeah, I think the most important thing that AI can help in medicine is probably in basically predicting the patient's future. So in every other discipline, right, you run simulations, right? If you were in engineering and you said, let's go build a bridge, your first thought is that I'm going to get some pillars and whack it into the ground. Right? You run simulations, you run calculations, you say, this is how much bridge I need, this is how much materials I need, how long does the bridge have to be, how tall does the bridge have to be, that kind of thing, right? If you were a chemical engineer and you were designing some new process, right, you would say, what is the thing I'm trying to make? What boilers do I need? What temperature do I need to put it at? And that kind of thing. What reagents do I need? You can just go, I'm going to start mixing crap. Right? Whereas medicine is very much the art. Right? It's this. That's why they call it a practice of medicine. It's not the engineering of medicine. Right? It's very much. This is a patient. You look at the X-ray and you go, there's some white stuff at the bottom. It could be infection, but it also could be heart failure. Not really sure, so I'm just going to give them antibiotics and see if they get better. Literally, this is the conversation that we have all the time in medicine. Right? There's so much uncertainty. Right? You look at a patient and you go, I have no idea whether or not this is this disease or this is the other disease. So, there's this concept of what we call a challenge in medicine, right? Where we do a fluid challenge or we do a fusimide challenge. Right? We just give them the treatment and see if they respond. Right? So literally, we just go out there and just start whacking and hope that it helps. Right? And this is obviously suboptimal. And I think one thing that's really good for AI is that AI is really good at predicting things. Predicting things is an easy format for deep learning because its input is the present state, output is the future state. Right? It's a well-defined problem. It's an easy label. The answer is the future, right? All you need to do is just collect enough data for that to happen, right? And so AI can actually quantify that, right? It's not just my gut feeling that I think that this is probably more infection, so I'm just going to give it some antibiotics and hope for the best, right? You can actually say, I'm 80% sure, right? The simulations show that 80% of people who present in this way have a lung infection, right? And so I can be more numerically certain about it. And I think that's where AI is going to be a big game changer, essentially.
Yeah. And so I guess what are the actual current barriers to making that reality?
Yeah. Like I said, it goes back to the data, right? So if the problem is input data, input state of the patient, and then when you're trying to predict its output state of the patient, and the question is, how do you get the states? Right? If the state is an X-ray now and trying to predict the X-ray later, right? You need to get two X-rays, right? And you need to link them up, right? You need to say, what if the patient took an X-ray in Melbourne, flew to Sydney, ignoring the coronavirus guidelines, took another X-ray in a different institution? How do you link those two up, right? And one of the problems we have in medicine in the Western world is there's a very strong concept of privacy, which is a good thing. And that means that patients own their data most of the time. And so they have this idea that if you're trying to access data of a specific patient and link it to a different data set, it's often difficult. There's no unifying linkage. There's no single identification number that you can go. And so that's the big challenge, right? It's curating this data, getting a consistent data set from multiple sources. It's very fragmented in healthcare, especially in Australia. But also in many places around the world, right? There's no one single source of truth. Right? It's not like if you're trying to predict, for instance, the risk of somebody defaulting on their mortgage in the future. That's simple, right? You go to one source. There's a bank. They've got the credit card statements. They've got their mortgages. They've got everything, right? That's easy. Problem solved. And probably usually the bank also owns some insurance company, so you can probably get that too. Right? But in healthcare, right, if you want to get this, you need to go to the radiology company, you need to go to the hospital, you need to go to the GP that the guy sees, you need to go to the Sydney emergency department that the guy presented to after thinking he's got coronavirus. Right? Now, there's all these different people you have to contact. Right? And it's just very, very difficult to organize that data into a structured form. It makes it even worse that the formats aren't standardized most of the time.
So I think we can move on to this last question. And so this is just for sort of the people who've been watching and sort of, having interested in in AI, sort of like what sort of like opportunities or like sort of thing they should do like to sort of like figure out if AI is actually something they do want to go in?
Yeah, I mean, fortunately, I think a lot of this stuff is opening up. In the past, when I first started in 2015, it was 2 years before somebody released any kind of medical data set that was useful for deep learning, which was the NIH X-ray data set that I talked about before. Then fortunately, there's heaps of public data sets nowadays, and there's lots of competitions and lots of money in there. Yeah, so what I was saying, there's lots of Kaggle competitions now that are medically focused. If AI and medicine is something that you want to do, just pick up a Kaggle competition and join it. I'm actually going to be hosting one later towards the end of this year in Rochester Express.
So, like, what is Kaggle actually like? Yeah, like, so I guess for someone like who doesn't actually like hasn't really heard about AI before this, like, like, is there sort of like, yeah.
Yeah, so Kaggle is a website with, basically lots of data sets, lots of competitions, and people all over the world compete to try and predict things, right? The good thing about Kaggle is that not only does it give you the data, it also gives you the resources to do it on. Right? They give you GPU kernels, GPU notebooks, graphics cards, and that kinds of stuff. That means that all you really need is a browser, right? And they even have tutorials on how to use these things. So literally just go to your browser, type kaggle.com, and go to the startup competition and press start. That will teach you everything you need to know.
Yes, I think that's it for our set questions today, and I think we can move on to our viewer question. So, so I have one just now, and it asks, so is there a problem with using AI medicine in that we lose the human contact or human care consultation?
So I don't think the human part will ever be lost. So the doctors are still going to explain the diagnosis. They're still going to have to treat the patients. And where I think AI will be useful is in basically getting out the negative cases, right? So people who don't have any diagnoses, people who are negative, it's possible that in the future humans might never need to look at their scans, right? You might just get a negative result, everything is clear. And if something is positive, then obviously we go to humans for further deliberation. But that means that we can screen a much larger number of people, right? It means that one doctor can effectively read 20 or 30 scans, 29 of which are normal, and they just have to deal with the one positive one, or the 2 or 3 things that the AI flag is positive.
Yeah. And another question is about the Magic Cup. So it says, I noticed that you entered and won Microsoft Magic Cup 2014. What advice would you give to students thinking about entering?
I would say go for it. Magic Cup is a great experience. You get lots of support from Microsoft. You learn a lot of things. It's a really good experience all around. There's literally no downside that I can think of from participating in the Magic Cup apart from the time that you spend on it. I would encourage you to bring a cross-disciplinary team. And if you're going to get an idea, it's always good, like I said, to get someone who's got the problems, where you have the solution, rather than you coming up with a solution or you coming up with a problem by yourself, essentially.
And I guess just a question the competition seems I guess it seems pretty daunting to actually enter a huge competition and kind of just have to speak to all those important people like so I guess just for people who might not usually actually put themselves out there and actually join competitions, what sort of advice would you have for just people who don't usually actually just really enter any competition?
So the competition is all about it's all about having a interesting angle on a problem. So it's the combination of having an interesting problem and an interesting solution. The execution of the actual solution obviously is given points, but you're not expected to solve the world's problems. Right? My advice to you is to treat this as, if you're trying to enter it, treat this as trying to find something that is interesting. Try to find an interesting angle, something that someone hasn't thought of before. Novelty is always really important in these competitions. I think my main advice would be, don't be afraid. The people who you talk to are essentially people like yourselves, just older. I'm not that different from you guys. I'm just a few years older. That's all.
I think for our last live question, someone just asked, how can AI help in data prediction, especially for the current COVID crisis?
COVID is a tricky one. I will go on the record saying that I don't think that predicting whether or not somebody has COVID is that useful. I think AI is much better suited at things like triaging patients, working out whether or not someone's going to have severe COVID sickness or not. We know that, for instance, lots of people are asymptomatic, lots of people are mildly symptomatic, and only a small percentage of people go on to be severely ill or die. Right? And one of the interesting things is, there's clearly a genetic predilection, but there's also probably some other markers or some other information that we can get about the patients that can predict this outcome. So, if you can, for instance, take an X-ray of a patient and work out whether or not they're going to need intensive care, right, from a very, very early point in their admission, right, that can be a big time saver. Right? You can say, you know what, I know you can tell a patient, I don't think you're going to be that sick. You can say, I don't think you're going to need intensive care. You can say, I know you feel really bad, but you don't have to stay in hospital, right? Which is a good thing. It frees up resources. But by and large with COVID, I think that's going to be the major role of AI.
Okay. So I think that'll just wrap up our webinar today. We hope you guys enjoyed this episode. And if anyone had more questions, is there anywhere someone could reach you?
You can always email me. You've got or LinkedIn me. I think, Evan, you've got my details. I'm happy for you to distribute that out if you want. There's always research projects at Harrison that you can participate with. There's also research projects at various public hospitals at the outfit where I work at. So if you're interested in contacting clinicians to see if there's any problems that you can help solve, feel free to reach out. Okay.
So thanks everyone that's watching. If you want to keep updated with future MYMI webinars, you can just follow us on social media and subscribe to our mailing list. So thanks again for joining us, and hope everyone has a great evening.